Hi everyone. In this video, we're going to be looking specifically at heat calculations, that is determining the amount of heat or affiliated mass or change associated with adding or taking heat away from a chemical system. So the three equations that we're going to be dealing with can all be found right on reference table T down near the bottom. You're going to see these three equations duplicated right here. And what's nice about table T is that it defines every single one of those variables for you. So if you ever forget what any of those things stand for, it's right there for you. This is going to help pull out specific components of these equations. When you run into them in word problems, we can figure out what type of value to plug in for which variable. So first, let's get a sense of where we might use these particular equations. The very first one in blue, as I like to call it, the MCAT equation, tells me that heat required to make a change in temperature is dependent on the mass of the substance we're changing, its specific heat capacity, how hard it is to get it to change temperature, and the amount that we want to change the temperature. So if we're looking at a heating curve, there are three spots along this curve in which temperature is changing at all. That's when it's a pure solid, a pure liquid, or a pure gas. Those slanted areas of the curve are always going to be where we use our MCAT equation because it's the only places on the curve in which temperature is changing. Those are the easiest to pick out. The other two types of equations deal with those flat areas. You're either looking at the heat of fusion or the heat of vaporization. Luckily for you, fusion starts with F, as does freezing, which you guys know means moving from a liquid to a solid. And that change in the arrangement of particles requires a certain amount of energy to be taken away to go in this direction. Well, you can imagine it would take the same amount of energy to be added back in to make the change in the opposite direction. So HF, or heat of fusion, has to do with the amount of energy required to make the change between the solid and the liquid phases. So if your substance is melting or freezing, you're going to be using the equation Q equals mHF to figure out how much heat was either absorbed or released during that change. You can tell there's only one more blank spot on our curve, and that's going to be for our third equation, Q equals mHV. The HV stands for heat of vaporization, and I see the word vapor right in there, which tells me it has to do with gas. So to vaporize something, we need to take its liquid form and turn it into a gas. That's going to take the addition of a certain amount of heat. You can imagine removing the same amount of heat will get it back to its liquid phase. So heat of vaporization is where we're looking at changes between liquid and gas. So that boiling and condensing line on these particular types of heating curve diagrams. Once you have this in place, you can use this diagram to help you with any word problem. I want to take a look at two examples with you. So first, let's go with this guy. A sample of water releases 542 joules of energy as it cools from 80 degrees Celsius to 45 degrees Celsius. What is the mass of the sample? Well, first and foremost, we need to know where we are along our heating curve. So the easiest way to do that is to just go ahead and draw a heating curve to pick out where it is we're at. What I notice is that the problem is telling us that it's cooling from 80 degrees Celsius to 45 degrees Celsius. So along my curve, I must be in an area where I'm changing temperature. And I know I have a sample of water, so I must be in the liquid phase. So I'm somewhere here on my graph. And you guys know when we're changing temperature, we're going to choose the equation Q equals mc delta T to do any calculation work. So now we just need to pull out where all those variables are in the problem. So I see some important numbers here, 542 joules of energy. Remembering heat and temperature stuff, joules is a measurement of energy, and heat, or Q, is what we're going to use to represent that type of measurement. When we have degrees Celsius, we know we're working with temperatures, and our temperature is decreasing. So that 80 degrees to 45 degrees represents a change in temperature. And what I'm wanting to know from this problem is the final mass of the sample that was cooled. So I've got a Q, I've got an M, I've got a delta T, and I know it's this equation that I'm going to be working with. So let's plug stuff in so we can figure out exactly what mass we're dealing with here. So I know that Q is 542 joules, and I know that that equals our unknown mass times C, which is the specific heat capacity of water. That's not something you need to memorize. It's right on table B alongside the heat of fusion and heat of vaporization of water. You're going to find that that's 4.18 joules per gram Kelvin. And what that tells me is how hard it is to get water to change temperature. And I need to know finally how much the temperature is changing itself. Well, I'm going from 80 to 45, so that's a change of 35 degrees. That's my delta T, is how much the temperature itself has changed. So I need to solve for M, so I'm going to have to divide everything by all the stuff attached to M, 4.18 times 35. And I'm going to do that on both sides of my equation. You're going to plug this into your calculator, and hopefully you're going to get a value for M in grams that makes sense. When I let my calculator do the work, I got 3.7 equal to my mass. And since it's a mass, I'm going to record it in grams. The hardest part of this problem was just picking out which equation to use. The rest is just pulling information from your problem or from your reference table to help you out. So let's take a look at a second example. In this one, I've got a 10-gram sample of water. Immediately, grams, I've been given a mass. And it's melting completely. I need to see melts as a phase change, so I'm going to circle that in case it helps me later on. It's melting completely at its melting point. Calculate the heat required. Whenever I deal with heat, that's a Q. Let's draw the heating curve to try and figure out exactly where we are. This word is what's going to direct you with what to do in this problem. It gives you no change in temperature, but that's okay because we're melting. So that puts me right here on my heating curve. Temperature stays constant. That change between solid and liquid is a Q equals MHF kind of change. So let's just plug and chug as we did before. In this case, we're given no information about joules. That's what we're trying to calculate. So Q will remain as my unknown. I pulled M out of my problem as 10 grams. HF isn't given to me in the problem, but again, it's on table B, right with the other information about water. And if you look up HF, you're going to find it's 334 joules per gram Kelvin, which tells me a little bit about the strength of the intermolecular forces of water. Doing the math, what this tells me is that it takes 3,340 joules to make this particular change for water. If you really want to be fancy, you can convert this answer to kilojoules. I recommend just keeping things in joules to keep it simple. If you really want to know, 1,000 joules is equal to 1 kilojoule. I don't have 1,000 joules. I've got 3,340 of them. So I must not have 1 kilojoule. I have some unknown number, which just lets me know that if I divide that 3,340 by 1,000, then X is going to equal 3.34 kilojoules. This unit is not going to show up all too frequently, but just so you're familiar with the idea of changing between joules and its kind of bigger brother unit, the kilojoule. But I really want you to focus on being able to get to your answer in joules because that's going to be the most common end goal for these heating calculation equations.